Hi guys, today we are going to start talking about chapter 4, which has all to do with forces. So forces actually span two chapters in your textbook. The first one is going to be kind of a review from AP1, and then the next chapter is going to be some more in-depth problems, more complicated problems that we're going to do on the AP Physics C level. So this PowerPoint should serve as a review for you guys as we go through it. I know it says 2013, 2014. There's a date. Don't pay attention. As we go through it, I would really like for y'all to take the opportunity to maybe pause it a few times and try to work the problems out on your own before you see my solution. Just to kind of see how much you know and what exactly you need to review. So these are some things that you need to remember from last year. Primarily Newton's 3 laws of motion, which most of you guys know already, that the sum of all the forces on an object is called the net force, and that equals ma. The weight of an object is the force of gravity acting on it, and that we have four fundamental forces: strong, weak, electromagnetic, and gravitational. How to draw free bodies, we're going to do a few today, and the difference between contact and field forces. So last year we did discuss the spring force, but this is just a reminder of what the spring force is, since it's kind of special. The spring force is a force that describes helps to describe the motion of an object attached to a spring, and it's a restoring force, right? So that means that it's always going to act in the direction opposite to the motion. So if I extend my spring here and pull it out a distance x, my restoring force is going to want to pull it back to equilibrium here in the center. Same thing if I compress it, right? If I compress my spring inwards, the spring force wants to pull the spring back out to sit at equilibrium. So that's why we have this negative sign here in front of our k, which is our spring constant. It's just telling us that those two things are acting in opposite directions. The force and the direction that you're either extending or compressing the spring will always oppose one another, and this is Hooke's law. I had a brain fart. Okay, so here's an example of doing forces using ijk vectors, which we discussed last chapter. So we have two forces acting on an object of mass 0.4, and the first force has a ijk vector notation of 2I minus 4j, and the second force is negative 2.6I and 5j. So the question is asking what is its position vector at 1.6 seconds, and then what is its velocity vector at 1.6 seconds. So if this was just a normal number problem, it would be pretty easy, but since it's in ijk notation, I just wanted to do it with you guys so that you could see how this all works out. So solution-wise, the first thing to do is to find the object's acceleration, and you're going to do that by finding an expression for the force on it. So here's force 1, we're going to add force 1 and force 2 together. So force 1 in the I direction we had 2, and for force 2 in the I direction we had negative 2.6. So you add those together and you get an I force of negative 0.6. You do the same thing with the J direction and you end up with 1. So now we have the object's force, we can find its acceleration. So all we would have to do is divide both of these terms by the object's mass, which in this case in the problem is 0.4. And we divide 0.6 by 0.4 and 1 by 0.4. This is our acceleration vector that we get once we do that, which is going to be super helpful to us because we can do some kinematics to find its position after 1.6 seconds as well as its velocity. So, position, kinematics-wise, from rest is 1/2 at squared. So we're just going to find the position in the x direction and the position in the y direction, and they told us the time was 1.6 seconds. So essentially your position vector, which your book likes to label as r, will end up being 1/2 negative 1.5 times 1.6 squared, and that will be in the I direction. And then we're going to add that to whatever the position is in the j direction using same kinematic, but with the j acceleration. And we get this guy as our result. So you can do the same thing for the velocity vector. So the velocity vector, we can use this expression, right? Because normally it's v equals initial velocity plus at. But we're saying there's no initial velocity. So we can do the same thing that we did up there for our velocity vector. So the acceleration in the I direction is negative 1.5, and the time is 1.6, and that's in the I. And then in the j, we have 2.5 and 1.6, and that's in the j. And then our answer is negative 2 for I hat plus 4 j hat there. So this is just a super quick review of IJK vectors and kind of how they can work with forces and acceleration and kinematics and all that fun stuff. So let's do a review of Hooke's law and spring constant. So here's an example of a basketball player that's hanging on the rim following a slam dunk. Prior to dropping to the floor, hangs motionless with the front of the rim deflected down a distance of 15 centimeters. So assume the rim can be approximated by a spring and calculate the force constant. So we're going to just draw a little free body. So we have the weight of the basketball player, right, pulling down on the edge of this hoop that we're going to say is acting like a spring. So his mass is 85 kilograms. So that means that his weight, or the force of gravity acting on him, is about 850 newtons. And so that is the force that is extending our spring. So if we look at our spring constant, or our Hooke's law, we have F equals negative kx. So negative k, and then it's being deflected downwards by 15 centimeters, so that's going to be negative 0.15 for your x value here. And then we can, oh, that should say spring constant, not force constant. Sorry, guys. That doesn't make any sense. And then we can divide both sides by negative 0.15, and we should end up with a spring constant of about 5.7 times 10 to the third. That'll be Newton meters. So pretty easy. Okay, here's an example of forces at an angle, and this is probably a good example of one of the harder AP1 problems that we have, just because of the way that the forces equal out and even out. So Mackenzie is pulling a sled, so here's our sled, and she's going to pull at 125 at 20 degrees to the horizontal here. And then the mass of the sled is 50, and there's no friction. So we're not going to get into friction until the next chapter, so we'll deal with no friction for right now. Find the acceleration of the sled and the normal force exerted by the surface on the sled. So let's go ahead and draw ourselves a free body. Remember, we always just draw a little dot. What forces do we have? We have the weight of the sled going down. We have the normal force between the sled and the ground pushing it up. We have an applied force, which we can just call FA right there. And then there's no friction, so there's nothing happening over here to the left. So let's go ahead and label what we know here. This is 500 newtons for your gravity. And then we have an angle here of 20. And this is 125. Now, the reason why I say that this is a little bit harder of an AP1 problem is because a lot of students will not see that the force that I'm pulling up here with is actually contributing a little bit of the normal force to the situation, right? Because it's acting at an angle, we have a force in the x direction and we have a force in the y direction, right? The components of this 125. And so what ends up happening when I split it up here in a second is that the x direction will end up being our applied force, or the force that's actually making the sled move, and then the y direction will actually be compensating a little bit of this normal force. It'll be taking a little bit of the work away from the floor, right? Because that's what the floor is doing here, is it's pushing back up on the sled and keeping the sled on the surface of the ground. And so if I'm pulling up a little bit on the sled, I'm essentially taking a little bit of the weight of the sled off the ground, so the normal force doesn't have to be quite as much. So your vertical force here, when you do your 125 sine 20, is 42.5, and this guy is about 117.5. So I always tell my students to redraw your free body diagram after you split up your forces. You got 500, you got 17.5, you got 42.5, and then you also have the normal force there. Sorry, that ended up crooked. So some students will look at this picture and automatically say that the normal force is 500, but it's not. It would actually be 500 minus 42.5. So the difference between those two gives me a normal force of 457.2 newtons. All right. The acceleration then, their net force, since your up forces and your down forces will just cancel, is 117.5 divided by the mass, which is 50, which gives you an acceleration of 2.35 meters per second squared. All right. Another example here we can do. While riding in a car, you hold out a necklace, and in front of you, in an attempt to find the car's acceleration as it takes off from a stoplight, the necklace makes an angle of 17 degrees with the vertical. What is the acceleration of the car? So I need to get a bigger space to do this. So here is your necklace, right? And then here is the vertical. And they're saying it makes an angle of 17 degrees. So that's all the information that you're really given at the moment. So the first thing you want to do is draw a free body. You have the weight of the necklace, and then you're going to have the tension force. And those two things should be straight in your mind. And then this is 17. So it might not look like you have much to work with, but you actually do. So start the process, right? You guys should learn that everything that happens at an angle you want to split into components. And then you want to redraw it. That should actually, I guess, be pointing that way. So what you're going to have here is that the y part of your tension, this vector right here, should cancel out with your weight. Those two things should be equal and opposite. And then what you have left over is your force of tension times sine 17, or sine theta, we'll just say sine theta for right now, is going to give you your MA, or your acceleration. So in the y direction, it should be ft cosine theta equals mg, or your weight. All right, so what you want to do when you have to solve these problems is you've got a lot of unknowns happening here, but that's okay because everything's going to kind of end up canceling out. So what I want to do is I want to find a way to talk about tension. Since I have tension in both of these problems, I want to find a way to talk about my tension in terms of the other variables. So here, my force of tension could be equal to mg over cosine theta. So I can do a little equation substitution here and plug that in there. So I get mg sine theta over cosine theta equals ma. And now I'm going to have a mass on both sides, so those just end up canceling out. And sine divided by cosine is tangent, so I have g tangent theta is equal to my acceleration. Now I know what g is because it's constant. I know what my tangent, or what my theta is, because it's told me in the problem. So 10 times the tangent of 17 will give you your acceleration in this problem, which is 3.05. Doing this process here, where you had to talk about a variable in terms of other variables, that was like the exception in AP1. We didn't really do that too much in a lot of our problems, but in APC it shows up a lot. So get really comfortable with having to do some systems of equations or manipulations or whatever you think you may have to do to solve a problem. All right. So I want to do this one with you real quick, and then we'll stop the video for today. So picture weighing 15 newtons supported by 2 wires, tension 1, 20 degrees, and then tension 2, which is 70. This is obviously not to scale. This is 20, and then this is 70. T1, T2, and then here we have the weight of the picture, which is 15 newtons. Okay, again in AP1 we did a lot of these problems, but they were all equal angled problems, meaning one was like 50 and the other one was 50 or whatnot. But here we actually have a situation where we have two different sizes of angles. So this guy's components go like this, and then this guy's components go over and down. But what needs to happen in order for this picture to be at equilibrium is that T2 cosine 70 should equal T1 cosine 20. These two horizontal forces have to be equal and opposite, right? If they're not, then the picture would slide to the left and right, and that's not what's happening. So that means that the vertical parts of both of these forces here added together should equal your weight. All right, so let's start some fun equation substitution. I have T1 and T2 in both equations. That means I have two unknowns, right? So I need to take this formula and rearrange it for one of them and then plug it into the other. So when I did it, I said T1 equals T2 cosine 70 over cosine 20. And now I have a way to talk about T1. So I'm going to put that in here. Just like that. So I can do sine 70 and then cosine 70 divided by, and then times sine 20. I forgot that guy too, because he needs to come down here too. So I can do all of that math in my calculator, and I end up with 0.94 T2 plus 0.12 T2 equals 15. So once I add those together, because they have a common term, and then 15 divided by that, we get 14.1 newtons for your tension 2. And then once we know that, we can plug that back into any of these formulas that we want to up here, this one or this one or this one, whatever we want, we can figure out what T1 is. And when we do that, we get T1 equals 5.3 newtons. Okay, that was meant to be a super quick review on how to do force problems again, and how to do force problems whenever you have angles. So tomorrow we're gonna, or on Monday, we're gonna do a little warm up, and then we will do some practice problems. So have a good weekend.